All right. So to start things off, I figured I'll walk through this for us before we dive into like slides. So I updated the week 2 slides a little bit. So if you like saved them from last week, I just kind of meshed together what we didn't cover last week with what we were going to cover. So we kind of start off where we left off. We'll use a lot of the same files. We kind of jump into Stata originally. So that state cigarette tax, I saved it as a .dta file so that, I showed you how to import it and then save it so that we don't have to do that every single time. So that's going to be up there. PowerPoint was updating this morning, apparently, so I had to do that before we started class. That's why that just popped up, so sorry. So we'll kind of keep working with that file and then add in some other ones that should have already been up on Canvas as well. But this is kind of a reminder to open Stata when we're using it in class. IU Anywhere, it sent me right here. All right, so it sends me automatically to where it wants to pull open these files, but it's got Citrix. Even if you went through the process, I don't think you'll see this every single time since it's your personal device. But just in case you're using a different device, or I don't know, what somehow got wiped, we'll detect it. Okay, it sees that it's already been downloaded. We did all that last class going through. So we'll open it up. Now it'll send us to hopefully what might have sent you there right away, where it's got this apps kind of icon. The only one that we're going to be using is down here, Stata SE 18. We're going to open it up. Open the launcher. It'll take a couple seconds to think, and then hopefully we should be back. We're waiting. We're in Ballantine, so Wi-Fi is terrible. Also, feel free to put that on the OCQs. Not that I'm, don't I'll say it came from me. I guess I should be recording this. So I've got the file, or I've got the program. We said with this do file editor, that's where we're going to have all the code that we run saved. Or we're in class, we go to open once we're in this do file editor. Once again, it's that little notepad, right? We were using, oh, I have it saved somewhere. You guys, oh, here it is. Review of statistics, right? This is the file that we kind of started with last class. Open that up. We imported some stuff. I said I'm going to save it so we can kind of start with that today and just use that .dta file. And then we'll kind of do some of the, this additional stuff that we talked about last week. So where we left off was we were thinking about these random variables, right? So this is X, this is Y. A couple of things that we didn't cover last class that I wanted to go through a little bit, and we'll kind of get some practice with Stata here in a second. We'll do some more review. But before we jump into Stata, we'll just kind of do this, right? So anytime we've got two variables, so last class we talked about calculating means. Okay? Anytime we have more than one variable, we have two variables, we can also look at what we would call a joint distribution. So the example I was thinking about, I've got this data set, and I don't think we'll even use it today, but it's got a bunch of different of these I-step math scores. I think I might have alluded to this or showed you a snapshot or screenshot of this last class, but it also has class size. So thinking about, I teach these huge 300 B251 sections. Does performance in those classes, does it matter that you're in a 300 person versus a 30 person section? So I might want to know what's that relationship between class size and performance, math performance here, but it's the same idea, right? So I've got these two random variables. The way that we're going to calculate a covariance is we'll use this summation sign. Once again, we introduced this last class, start with the very first observation, go to the very last. Capital N was the total number of observations in our population data, right? We're then going to go through and take each observation's value for X for class size and subtract, what does this notation represent? Remember, mu represents the mean. So the mean of that class size variable. So every observation we're saying, okay, how much did their class size deviate from the average? And then multiplying that by how much did their math score deviate from the average math score? Okay. So basically, you can kind of think about this as when my class size and my test score are above the mean, what's true about the sign of that observation when we multiply those deviations? Well, if I'm above both of them, what would the first difference be? If I'm above the mean, then that difference is positive. If I'm above the other mean, that is positive. That was an observation that was an indicator that when my class size is high, my test performance tends to be high as well. That was an observation that was evidence that these two things are positively correlated. If they were both below the average, what would that indicate? Well, there, the difference from the mean would have been negative times a negative. Well, that was also an observation that when my class size is low, my test scores are also low, an indicator that these things are positively correlated. So we'll go through every single observation and do this. Now, for some of them, if my class size is above the average, but my math score is below, positive times a negative would actually add in a negative value. So it's almost like I'm looking across all the observations and saying, this isn't perfect, but do these things tend to be on the same side of the mean or on different sides, right? Now, this is going to be evidence only of like what we would call a correlation. It's not causal yet. We'll talk more about how we get to a causal relationship as we progress throughout the semester. But the first thing we're going to look at is like this correlation, right? Or the covariance. So sigma xy, that's just our notation. It's the covariance between that x and y variable, okay? Now, we won't often do this by hand. We're going to have Stata do this for us. What would the units of my covariance be? It's kind of weird here. We didn't really talk about this with the mean, but with the mean, if I'm adding up, let's say I'm finding the mean math score, what would my units be? Just points? What about on the mean class size? Units would be the number of students. What would my, same thing with the variance, right? We're just looking at the deviation, right? We're still in the same unit. If I have two variables here, what would it be? Points, or sorry, students times student points, right? So the covariance, like we're getting some kind of weird units there, and we can't really compare relationships across different data sets. So instead of the covariance, we go one further step and we calculate something where we can compare, say, is the relationship between class size and math scores, is that as strong or is it weaker than the correlation between maybe, I don't know, excuse me, parental income and math scores? Well, what would parental income math scores there? The units would be dollar points, right? So the units don't make sense. So how can we get rid of these units? Well, if I divide by the standard deviation of both variables, what that's going to do is essentially I've got students times points divided by students times points. It cancels out my units. Also, by dividing by the standard deviation, I account for the fact that there might be more variation in class size data than there would be for, I don't know, the number of credit hours taken. There's not going to be near as much variation. You all take pretty much about, I mean, not exactly the same, but the difference is only a couple credits, right? Difference in class size can be, like I in my example, hundreds, right? So this correlation coefficient will not only get rid of our units, it's a nice unitless measure, but it also accounts for the fact that there's just more variation that exists in some variables than others. And by dividing by that, we've accounted for that. We can now compare these relationships across different examples. Okay? So, end of the story, correlation coefficients are a lot more useful for us. But you'll notice, in order to calculate a correlation coefficient, what did we need? The covariance. Okay. So, this correlation coefficient, we'll use it. It's kind of somewhat related to our linear regression stuff we'll get into, which we won't touch on that quite today, but definitely next class. I shouldn't say next class. Next week, we'll touch on that. But that correlation coefficient is going to be somewhere between 1 and -1. 1 representing the strongest positive correlation, -1 representing the strongest negative correlation, right, we could ever see. Okay. I'm not going to waste too much time with this. Once we look at the actual data, I might work through a small example when we're in state of how to do this by hand. You aren't going to have to do this a lot by hand, kind of moving forward throughout the semester, so I don't waste too much time here. So we'll come back to that. But another way we can kind of visually see these correlations are just simply looking at a scatter plot of the data. Once again, I'll show you another example of this once we jump over to Stata. But if I were to plot every single point, so let's say I had a data set and I've got a bunch of different students, what their class size was and what their math score was. I plot every single observation. If I were to kind of draw a line that best fits this data, what would you say? If I had to just draw a linear line, looks like maybe something like that. It would be what? Upward or downward sloping if you had to look, if you had to say one. Upward. So that correlation coefficient or that covariance should be positive. Right? Now, like I said, I'll give you another example in Stata that will really show us this, but we can see this play out with scatter plot data. Okay. So instead of going to conditional distributions, well, we'll do that. We'll stop at normal and then we'll go to static because I want to spend some time there today. Okay. So one thing we didn't talk about last class, we talked about means, but we're also going to start to talk about conditional things. So conditioning on something, what is the mean? So here, I might be interested in the mean of y, right? So another way of writing out this mean, if it's a random variable, we said it's like the expected value. Right? So the expected value of y might depend on other values of x. Right? So in a very simple example, just to kind of reiterate this, we're talking about the mean of a variable. Typically, we use this notation when we have all the population data. It's really very similar to, for the sake of what we're doing, we can kind of think about another way we would write the mean is it's the expected value of a randomness. So if I'm choosing a person at random, what's the expected value? Well, it would be the mean. Okay. So the expected value of a certain variable, maybe this is, I don't know, the expected value of someone's GPA. So if I were to select one of you at random, what would the expected value of your GPA be? Okay. Maybe I think about this I don't know, maybe I think about every econ major for my example that I'm thinking about in a second. So if I took an econ major at random, what's their expected current GPA? Well, then I could say, well, no, sorry, not equal. What is their expected GPA given this other variable x, which is either just a 1 or a 0 if they've taken Econ E371, okay? And then maybe I can think about, well, what would the expected value of a student chosen at random be if this random variable x was a 0 or that they have not taken Econ 371, right? If this is a very difficult class, right, maybe the expected value of the GPA when someone has already taken 371, I don't know, maybe let's say it's 3.1. The expected value if they haven't taken it yet, well, if it's a difficult class, what we expect about the GPA for someone who hasn't taken it? I don't know, maybe it's a little bit higher, right? So conditional on this other piece of information we have, here it's just a simple 1-0 variable, right? Did they take E371 or not? The expected value or the mean of the variable we're interested in GPA could be different. So this is the idea that means, right, could vary depending on if we condition on other pieces of information. Right? So I think the example I use in the slides, we've got, instead of just like, did I take 371 or not? Right? Maybe I think about, well, what's the expected math score of an individual for someone who has a college degree or just a high school degree? So X here was the number of years of education, 12 representing a high school degree, 16, obviously it can take you a little bit longer or a little bit less, but just for the sake of this example to make it simple, 16 years would be that you have a college degree or an undergraduate degree. Well, there, maybe if I condition on the fact that they have a college degree, the expected math score is a little bit higher than if I was to choose someone at random who didn't have a college degree. Okay? So I know that this y variable, math score, depends on this other variable, which is how many years of education have they taken? Or in my other example, the mean of GPA depended on have you taken 371 or not? Okay. So let me see, do I have like other ones? You can kind of think about why is that useful? Well, just like the whole reason why I put this after correlations and covariances, correlations were telling us like the relationship between these two variables. If I were to look at this and I see that the mean math score is higher for those with a college degree versus those who don't, then the difference between that is really, in a way, telling me, well, what was the value of a college degree in terms of my performance on this math test, right? Well, on average, people who only had a high school degree scored 350. Those who had a college degree scored 354. So I could kind of think about the difference between those two being how many points having a college degree would add to this standardized math test. Or in my other example, I could think about the correlation or this relationship that exists between GPA and whether or not I've taken E371. What is the effect of taking E371 on my GPA in my example? It has, on average, decreased it, No, I'm trying to ask you crazy hard questions here, right? We've decreased it. So we're starting to get at, by thinking about this difference in expected values based off conditioning on something, we're moving towards identifying causal relationships, right? Right now, they're just correlations, right? Because maybe the people who have taken 371 already, maybe they were smarter to begin with, right? We haven't factored that in, right? But this is kind of our first like quick glance at what the effect of this other variable is on the variable GPA that we're interested in, or what the effect of years of education was on the variable we're interested in, which was performance on this math test. Okay. Any questions on this before we keep moving? Shouldn't be too bad. So we've got this definition of independent events. So before I pop this up here, if two things are completely unrelated, so let's say this math test is supposed to measure aptitude that is independent of like what math courses you've taken, right? So somehow it's measuring like speed and very basic math that everybody knows. If these two things are completely independent, this math score, my performance should be the same no matter how many years of education I'm taking. It's more of like an IQ test, right? It's measuring my aptitude, my innate aptitude for learning. What would the difference in the expected value of the math score be if they're independent completely? If education doesn't impact at all my IQ measure, right? It should just be that difference is 0, right? Or, right, that the expected value for y, regardless of what the value for x is, it's always the same. Right. So if I were to choose a person at random here, and let's say I want to know what's your expected GPA given, and the x variable I'm looking at is, I don't know, the length of your hair. Right? It's a variable, I can measure it. I would think those are completely independent events, right? And so it should be that no matter what length I see your hair be, the expected value of your GPA should be whatever the mean GPA is. Those would be completely independent events. They would also end up having a correlation coefficient of 0. Okay. Any questions on that there? All right. So I kind of already drew out another example, just thinking about when we're looking at the expected value or the mean of these different variables, we can condition on other things. Okay. Can be conditioning on the years of education, a 1-0 variable, whether or not you've taken a course, or in my other example, the length of your hair, right? We could actually come up with an expected value for GPA for if your hair was 0 inches, 1 inch, 2 inch, 3 inch, 4 inch, 5 inch. We come up with a ton of conditional means here, okay? So we're going to stop at the normal distribution, and I want to look at how we do some of this stuff in Stata, okay? So we left off last class, and I think this file should be updated on Canvas here. So if we're going, oh, there's Canvas. So if you click on this review of statistics, do file, in fact, I second guess myself sometimes, but we'll make sure. I believe I got this. Let's see. So review of statistics should be under week. Where is that? No, did I move it to week 2? Oh, where did I put it? Oh, it's under this week 1 data files. There we go. Right. So 13th would then. Let's just make sure it's updated. Make sure we all have it. Yeah, 13. It's the same file. There we go. So I've got the same file kind of is existing up there. Once again, it's probably easier just to find it from the home page. Right. That review of statistics file. I think I put it in still in week 1, right? Because we started opening it or working with it last week. So we stopped here. I'm going to remind us, where is it at? There we go. So we're going to go down here to line 19. We're going to set this file path. So hopefully I've got this set correct because I have it set where I was using last class, which is my OneDrive or this iDrive. And I had mine under a bunch of different folders. I said for you, if you were to just drop this on your iDrive, you wouldn't have any of this, right? The file would just be on your iDrive, but this would be your global path, okay? So you can kind of go ahead and set that, right? I'm then going to use this use command, which says just open this data set up. using a $sign and right, my kind of squiggly brackets, and then whatever I define my path to be, here I just chose the word path, it should open up this state cigarette tax.dta file, as long as I've downloaded that from Canvas, that's the one that I made sure we had here for week 2. Okay. Now, if you downloaded this and you don't want to worry about the code here for a second, no. Did I accidentally click on that? Okay, good. Because sometimes I'll take it a long time. I could just go to File, Open. Go to my week 2. Oh, did I not drop this on here? Probably not. There it is. So here I've got that .dta file already there. Instead of like doing the global path, I can just find it using the File Open method. And notice it'll put all of that in there for me. So either way, right? And then, I might copy this, paste it over here, just to kind of give you a comparison. These 2 lines of code are really doing the same thing, because the file path that it's using is the one that I've already defined, right? So it's just whatever makes more sense to you. If you just want to use the File Open method every single time, that's fine. I like to kind of get used to using these file paths, because not only is it applicable to this class, but if you want to start to learn things like R, Python, like you might start using some of this, right? So it's not as clunky. You don't have to go through the process of finding where that file exists every single time once I know that it's under this file path, okay? Is that any questions on that? Are we getting that opened up okay? Anyone having trouble getting that file open? Anyone having trouble getting on Stata here today? Yeah? What is it giving you? So were you here last week?
I wasn't.
Okay, well, that looks good. We can talk after class. For those of you who were here last week, how many of us are having problems getting this open? Okay. Yeah.
Do we need to delete your old lines of code with like your?
No, you can just keep it. Yeah. So what I'll end up doing in class is I usually run this line by line. If you try to, for instance, if I were to have nothing selected and I go up here to execute, it's going to try to run this entire do file, right? That makes sense sometimes if like you kind of stop working and you want to pick up where you left off, because even if you close the program, you can now just get back exactly to where you're at. In terms of the files you use in class, probably won't make sense for us just to run it, because I'm adding things in here and there to show you different things. So I'm not ensuring that it will run all at once. I'm ensuring that you have evidence of code that you can. Does that make sense? So for us, we kind of did some stuff last class. Today, we're starting right here. So I guess if I really wanted to be, I could delete everything, but I want to make sure this is all in the same file. So we'll go back down here. Once again, I could use that global path, or I could use this new line of code, which is what it gave me when I just did the manual of just go to File, Open, and select the file. Now, if I try to do this, I'm going to get an error. Oh, no, I'm not. I should have gotten an error, which is, I think it's because I'm using the same file. If it's trying to like upload a new file, sometimes it'll want you to clear it out. So sometimes we need this clear command in here. I'm surprised it opened it without it. I think it's because I tried to execute the whole new file, and so it just threw everything out of memory. But let's say I had a file open, right? So how do I tell if I've got a file open? What icon do I use up here? Do we remember how I can look at the data? Magnifying glass, right? I'm looking at the data, right? That's an easy way to remember it, right? So if I'm in this do file, I've got something open. If I try to run and open up a file without clearing it, well, it's still open. It must be because it's the same file path and everything. Okay. Sometimes, especially if you're trying to open a brand new file, not state cigarette tax, it'll give you an error. I just always default to using that clear command. That way, if I'm switching from data sets, it clears out, gets rid of the old data, uploads the new one. Okay. All right. We talked a little bit about this last class, although there's no reason for us to kind of drop any observations yet.
So did you just copy and paste the state sig tag? I'm just confused how you got
This
24. Yeah.
So when I went to File, Open, and I open this file, right?
Yeah.
It puts that line of code in there for me. So this is code that's being ran. If I want to save this for later use, if I close the program now, this goes away. So I guess you can't see me. I guess I should do it this way. I'm using shortcut commands on my keyboard. So I highlighted that, I copied it, and then I went over to my do file to make sure that I have it for later use. And I pasted it. So I apologize. If I ever do anything like that, it's a little bit bad practice of me. I should try to use that mouse so that you can see I'm copy pasting. I was using the keyboard shorthand or shortcuts, you know, Control C, Control V. Any other questions up to this point? Okay. So I've got this data set open now. Do we have any other issues? Because if I keep going and you're left behind, that doesn't help me or you. Yeah.
Is there any advantage of doing the global path and views rather than just like?
Not necessarily. Probably not for this class. If you're starting to run more complicated code, you're going to want to open different data sets. You're going to want to save things. It just speeds up the process because I can rerun the file every single time. I don't have to go to like file open and yeah, but yeah. I usually show that to you early on because I don't know where anytime you use my do file, do I know what your file path is? No, right? So I always write it using mine, but I set the global so that if you wanted to, you could just copy and paste your file path right in here, and that way it would all run accordingly. Otherwise, every time we get somewhere where I'm opening a file up, you're going to have to manually go through and do it. Now, if you already have the code in here and you just set your file path, now anytime I'm importing anything or I'm using or saving anything down here, you've already got the file path set. You don't have to worry about doing it manually. Does that make sense? Yeah. Any other questions at this point? Okay. So we'll skip down. We did this last class. We said we can use like the summary. Oops. Put this over here. I can execute. It gives me some summary statistics so I can calculate the mean of the state tax, standard deviation, variance, number of observations. Gives me a bunch of different information very, very quickly. If I were to do this by hand with 550 observations, it would take forever. We can do it very quickly in Stata. Okay. Now, another thing that I can do that we might want to do is I could create new variables that are equal to the mean. Okay. So for instance, here, I use this egen command. So it gets kind of tricky. I think I introduced the gen command maybe last class, like you can create new variables. I think that was all the way. Oh, maybe I didn't, right? So maybe I didn't save it. I'll do it right here. So create boring variables that don't really do a whole lot for us, right? So I'm going to create variable 1, and maybe I just set it to be equal to 1, right? If I do this, it's going to tell Stata, generate a new variable, set it equal to 1 for every observation. So if I go ahead and run this, and then look at my data, I now have this new variable, and it's a 1 for every, not very interesting, but I can start to add in new variables into this data set, okay? Now, what might be more interesting is instead of just a variable that's all 1s, because what does that mean? I'm going to create a variable that is equal to the mean of this state tax variable. So sometimes instead of gen, you're going to have to use this egen command. So gen is just if I want to generate new variables that are equal to value. So anytime I'm doing like basic math, I can use the gen command. So maybe, for instance, I look at this data set and I want to take, let me see, let's do tax per capita. Well, maybe I want to do a ratio of the tax to the cost per pack. So I've got two variables, cost per pack and tax per pack, okay? So I can create this new variable. I'm going to just call it ratio. Okay. Well, no, I'm going to call this variable ratio. And I'm going to set that equal to the tax per pack, if I can spell, divided by the cost per pack. So this is kind of like what proportion of the pack of cigarettes is coming from taxes, right? So anytime I'm just doing basic math, I'm using this gen command and it will create a new variable. Now notice this one's a little more interesting because now for Utah, notice it's tax, it's almost like half, right? $2.70 out of the $6.20. Whereas like down here, only $1.50 out of the 480 is. So now for every observation, I have a different ratio for every state, right? Because every state's data is going to be a little bit different. So I can create these new variables using the gen command. I just have to make sure that when I'm creating them, I'm spelling the variable names correctly. That's a huge part of it, which seems dumb, but it's, case sensitive. So I have to make sure I know exactly how this variable is being spelled, okay? And I can do that by looking at this data browser. Okay? Yeah.
When I ran the second gen file with the var ratio, it said no data set memory has changed since last saved after the first variable 1 equals 1.
So did you call the variable the same thing?
No.
So what does your line of code say? Gen var underscore ratio?
Yeah, it's the exact same thing. But it just spit out a no data set memory has changed since last saved.
So maybe, let me see. If it's already defined, I can tell you. I can't troubleshoot everyone's individually, but I can tell you if you put this in there exactly, right, it should create that. So what are some issues? Like I said, if you accidentally already tried to run it twice, it can't overwrite. You already have the same variable. If for whatever reason, maybe you have a space instead of an underscore. But if you use the gen command, oops, right, call it this new variable name, 1 equal sign, exactly what we have here. If you're just selecting this and then executing it, it should create that variable for it. We run into future problems. I can take a glance at it here in a second, but I think that's probably what it's going to be, one of those issues. So this was the gen command. We'll use this a little bit as we progress. More likely, we're going to use something like this egen. So egen is basically allowing Stata to access a bunch of stored programs that are already defined. So it has stored in its memory how to calculate a mean. So I'm going to create this new variable or generate this new variable using a built-in function in Stata. So I'm going to call it state tax mean, right? So I'm going to egen this state tax mean. What is it going to be equal to? It's just going to be equal to the mean of this state tax variable, okay? So if I execute this line of code, it should create a new variable. Now this one should be the same for every single observation because all it's doing is calculating the mean of the state tax variable. So the mean is going to be the same for every single observation. So if I go ahead and run this, the mean state tax is 0.585 across all of these different states. And in fact, that should be the same thing I get when I use that summarize command, right? The summarize command was telling me the mean. It's just that it told me sometimes we'll have things in Stata where it gives us output, but that output's not saved anywhere. So if I want to actually save that mean, maybe I create a new variable, which I'll save the actual value of that mean as. That's what I was doing here, creating this new variable where now I can see, oh yeah, here was the mean of the state tax variable. Okay. Any questions on that? I can do similar things, create new variables. There's other built-in functions. So one of them is the median. The other is SD. What do you think this probably stands for? Standard deviation. So I can run these. It's going to create two new variables, the median state tax, standard deviation of the state tax. Sure enough, if I go back and look at those summary statistics, oh, that standard deviation is the exact same. Also, what would the median, where's the median in this output? We said the median is the value that there is. 50% of the data is above it, 50% is below. So that 50th percentile is our median. It doesn't specifically tell us that, but that's what a median is, right? It's the value that's the 50% cutoff for the data. So we've already got that information here. It's just now we've got it saved as different variables, okay? Now, why we would want to do this makes sense later on. I'm just showing you some different tools we have. Yeah.
How'd you get that table?
Yeah, so that was all the way back here. We did this last class. We just used that summarize command, state tax, comma, detail. When I ran that code, it gave me the summary statistics. Now, these aren't saved anywhere. It just spits them out so I can see them. Right? When we actually created the variables, this will save them into our data set. Okay. Yeah.
How do you fix the error that says no data set memory has changed since last saved?
No data set. So do you have, if you click on your web browser or your data browser, is there anything there?
What do you mean? Like,
How do I view my data? What icon do I click on?
isn't it window?
Not just asking you. Yeah. Magnifying glass. That means look at the data, right? If you click on that, do you see anything?
Yeah.
So you've got an actual data set open?
Yeah.
And when you go, you select this. Have you already created this variable?
I'm trying to right now.
So if you highlight it and click on this, it's giving you that error. Why would that be?
I had the same error. I just saved the file after running the first gen command and it fixed it.
You say you shouldn't have, hold on. So this shouldn't be how you do it. So let me think why it's giving that error. So you've opened the data setup. You've tried to run this code and it's just not letting you. Oh, did you open it up as a .dta file? Or did you import it as the CSV like we did last class?
As with that DTA.
So why would it tell you? As long as you have it open, it shouldn't let, or it shouldn't make you do that. Let me talk to you guys after class just so I can make sure I figure out why it's doing that, but that ultimately shouldn't be something that's happening. Bye. All right, so we've got these new variables, right? If we're running this code, we've saved these kind of as separate variables, right? So the next thing we can do, I kind of already showed you a snapshot of this, excuse me. But maybe I want to look at what is this relationship between cost per pack, right, and the state tax, right? Is the state tax, we know inherently in economics that we tax something that should cause the price to go up, right? So how much further up, right? What's that relationship? So you can go through, and this is where any code I give you, there might be user-friendly ways to do it. So I think here, let's see if I can remember. Statistics, summary table, descriptive, yeah, correlations. And so this is why I don't usually teach it this way, because I can't remember where everything is at, to be completely honest. Look at all these, different options, and I can't remember where everything always exists. Here it's under summary table. Yeah, and this is even the third, look at all this stuff, right? So summary, descriptive, correlations and covariances. We could come up with what variables. Okay, I can do a drop down. I want to know the relationship between cost per pack and that state tax. Hit OK. And it'll tell me like the correlation coefficient here. So there's ways of doing this. I could go graphics. I can create a chart where I add in, I do a scatter plot and I add in different variables. Don't worry about all this. Anything I ask you to do on the homework, I'm going to give you a line of code that probably makes it easier than trying to hunt down exactly where this is at. Okay? So if you wanted to create a scatter plot, this is going to be the line of code which you would use. So it's two-way, and then in parentheses, scatter, and then the two variables you want to scatter plot between. So in fact, I'll highlight this and just show you. And these, you don't have to do this while we're in class. These sometimes take a little bit of time for whatever reason. Data visualizations through IU Anywhere, it takes longer. So you can kind of see here, okay, unsurprisingly, what does that correlation between state tax and the cost per pack look like? That correlation is positive, right? So I can do that very quickly. Now, this line of code, instead of hunting it down, reselecting the variables every single time, I can also do things like, oh, I don't know, what are some other variables that are interesting here? So I could do tax revenue and then maybe state tax. So here, instead of cost per pack and state tax, maybe I want to look at how much tax revenue is generated why might this be interesting from an economic standpoint? If I increase the tax, what's that going to directly do to my tax revenue? Increase it, but when I increase the state tax, how much do people buy? What's that going to do to revenue? So what matters? I'm doing a real review for you econ majors. Something that starts with an E. So people will pay more, price goes up, quantity purchase goes down, elasticities, right? So this would be something like telling us where we're at in terms of what's the elasticity right now if we increase taxes. So, oh, this is kind of all over the place. This is harder to see, right? It's probably because different states are probably at different elastic points on their curve. We're getting something that looks like there's not a real clear cut. Maybe it's positive if I draw a line of best fit here, but it's not as clear. But this is a way we can look at the relationship between two variables pretty quickly using a scatter plot, okay? I might ask you to do that in that first problem set, right? Once again, if you really want to, Google search exactly where to find. The code's probably the easier way to do it, okay? I can also run correlations. This will give me the correlation coefficient. So what's the correlation coefficient between cost per pack and state tax? And I'm going to sorry, I got to get better at this. Copy and paste it. And then I'm just going to change this one to tax revenue. So I'm going to calculate two correlation coefficients pretty quickly. I'm going to go back here. Okay, I ran that code. What looks like it has a stronger positive relationship? The tax per pack and the cost per pack, right? It's not, it's a little bit weaker when we're looking at tax revenue. Right? And that's because we know that when taxes go up, people also buy less, okay? So anytime we have output like this from this correlation command, these are going to be the correlation of the variable with itself. Those should always be 1, right? We're interested in the correlation of the two variables with each other, which is this kind of, not the correlation on the diagonal, okay? Any questions here before we keep moving? Yeah.
Is there any way that you can find these commands instead of, just so we know?
Like correlate and.
Yeah.
So, I mean, it has a help and you can like search, I guess if you go search, you can search different commands in terms of what they're doing. That's kind of why I'm going through them right now, right? I'm telling you, like, if we want to find a correlation coefficient, I wouldn't expect you to know this or search for this. I'm telling you what determines the correlation coefficient, this correlate command. The syntax?
Yeah, just like.
You could probably, like I said, you could use that help file and search the correlate command and it would likely tell you. I try to walk through it here if you're ever not clear on the syntax, like you use the correlate command and then just the two variables that you want separated by a space. So if you're following along with what I'm doing in class, the syntax is kind of already in there in that do file. I'm never going to ask you to do something where you wouldn't have an example of what that syntax looks like. Is that what you were asking?
Yeah.
Mm-hmm. Any other questions? Okay. All right. We'll save this. Where are we at in time? So we go till 2, right? Yeah. We'll kind of deviate from this a little bit. So this looks like standardized stuff. We haven't talked about that yet. Let me think if there's anything else I want to do for you guys here. Any other questions for right now instead of, also, let me just, so we can troubleshoot this quick. What area were you in?
Yeah, so for like relational mapping.
Okay.
But for I try to run.
So you're clicking on the commands on the side there. Do you have the do file open?
Yeah.
Okay, so go to the do file. Actually, Gen. So yeah, go here. The Gen ratio.
That one got to work, all the others.
So if it's, now go back to the program. So it's already defined. You've already created.
Yeah, that was the one I was able to get. The others were showing up at all.
What?
Like this command, mean.
So you haven't used the mean yet, right? So
Okay.
this is where I would not open my own do file. When we're walking through these in class, I would be working off of the do file I give you on Canvas. That's why it's up there, right? When you're doing your own problem set, you'll have to open your own do file and start there, right? But when we're walking through the first time in class, it's probably going to be helpful to be using the code so you can follow along quicker with what I'm doing. Now, if I add things in, you can mimic that, type it into the do file, maybe save it as, review of statistics in class edits or whatever you want to call that. But I wouldn't start from scratch in class because it's just going to be it's going to take you more time. It's going to be harder to follow along with me. It's also more likely you get an error that I'm not exactly sure why. And it's probably because there was something in here that I ran that you don't have in your original do file. And I'm not really sure what that is because I can't see all of your computers, right? So when it comes to us working through these in class, I would be operating off of the do file that I give you on Canvas. Now, when it comes to your homework, obviously, you got to start from scratch because I'm not giving you a do file for that, right? That's where you take what we've done in class and try to apply it to a different data set, okay? But to the question earlier, the syntax for everything should be in this do file, okay? Any other question? I know it's tough. It's a lot, early on, getting used to this, but I'm trying to go slow. If you have questions, once again, office hours might be a good thing this week, especially once that first problem set is assigned. I'll probably put that up after Thursday's class. Might be a good idea to kind of early on stop by office hours, start those projects early so you can kind of get an idea if you're running into some of these issues where you're getting errors, things like that. Okay. All right. Any questions? I'm going to just put this in here so I remember where we left off. Any other questions before we jump back to the slides here? Yeah.
I just don't want to lose this. How do you like save it correctly? Just file, save as.
Yep. So file, save as. It already has do file selected, and then you're just save. Now, I would, like I said, you don't want to overwrite probably the one you're downloading from Canvas. Just like call it something else so you know that this is the one that you did edits in class on. That answer your question? Is that what you're getting at? Yeah. Okay. Now, what you shouldn't necessarily have to save is the actual data file. Why? Because as long as you save the do file, even if I clear out the data. So notice one thing, it's telling me I don't always have to use that data browser. It kind of tells me what variables I have. I just can't look at the actual observations. I just cleared this out. I've got nothing left. Well, shit, I got to start all the way over from the beginning. Well, that's fine because as long as I have this saved, notice I can highlight all of the code I currently had, right? Starting with opening the data set up, putting out the summary statistics, all of this. Run that, okay, created my scatter plots. Go back here, and I've got the data. I've got all these variables I created before. So this is why saving the do file is important, because then if I have to leave and go back to it, well, now I don't have to run it one line at a time. I can run all the code I had in there, right? So that's, one real big advantage or something that's really helpful of having this all saved in a do file, okay? Questions on that before we keep moving here? Okay. All right. So let's get over here. We're going slower than I wanted, so I'm gonna have to pick up the pace a little bit because this is gonna be a lot of review. So I'll try to get through this kind of quick, probably through the end of class. But you should hopefully notice this, right? So you guys talked about this in your 370 or equivalent, right? Normal distributions. Everyone's heard of this before? Yes. Okay. If not, let me know. This might be a problem, right? So some characteristics about a normal distribution is it's symmetric, right? So the mean is the same as the median is the mode. If I fold this distribution on top of itself, it exactly matches up, right? There's an equal amount of the data below and above the mean. Now, my mean can be any number. So when we're talking about normal distributions, it's not just one normal distribution. There's several normal distributions. In fact, I've got a couple examples here in a second, but things like rainfall, human intelligence IQ tends to be normally distributed. But there's all kinds of different normal distributions, and they're defined by two things. What is their mean? Also, this is class. I'm not going to try to get too upset about it, but let's try to keep the distractions in. All right, so we've got means, right? If I think about something like human height, I've got two nice normal distributions, but if I were to graph human height, just every single person's height, it won't look normally distributed. It'll look kind of weird. Why? if I were to do a conditional normal distribution, if I were to look at the average, or if I was looking at the distribution of height for men versus women, those are both normally distributed, but female height tends to have a lower mean, right? So we can have multiple normal distributions and they're going to be defined by their mean. That would like shift our distribution along that x-axis, okay? The variance of our distribution is also going to, we can have many normal distributions, but they have different variances, right? So maybe if I looked at, I think male height, if I remember right, tends to have a wider range, it has a higher variance. So even if we had two, normal distributions, the exact same mean, if one of them has a higher variance, what's that going to do to my distribution? A higher variance means that more of the observations are what relative to the mean? Further away. So it means that my tails are going to be further out. Well, remember, when we're looking at normal distributions, we're plotting these different values. What's on my y-axis? So these are the different values for x. Y is what? If I were to look at that one value, y tells me the probability I see that value. This is telling me that values close to the mean have higher probabilities than values further away. But if my variance is large, what's true about the values that are further from the mean? The probability I see them is higher, right? So if the data is more varied, I start to get these like fatter tails, right? The tails get fatter and kind of the peak of my distribution gets a little bit lower.
So the width of the distribution. That just describes the variance.
Yep. Any other questions? So the mean and the variance will define our normal distribution, right? So I kind of have an example here. If I were to look at this, do men or women have a higher mean height? Well, which distribution is shifted more to the right? Male height, right? Which of these has a higher variance? So if it's a higher variance, does that mean my distribution is more spread out or more peaked? More spread out. Higher variation means values tend to be further from the mean, which means that the middle part of my distribution will be kind of like less likely. So the shorter the distribution, maybe this is a less technical way of saying it, the shorter or more smashed down my distribution, the higher the variance. So who has a higher variation in height? Males, right? Women's distribution for height is a little bit more peaked, meaning they have a lower variance, okay? So another thing that we can kind of talk about, and we'll back out why this is probably more next class, but if I look at a normal distribution, if I were to go once, so we talked about standard deviations, we can calculate them in Stata. If I go one standard deviation to the left and the right of the mean for any normal distribution, it'll always be the case that there is a 68.3? Yeah, 68.3% chance that if I were to choose one observation at random, it's somewhere in between one standard deviation above and one standard deviation below the mean. Right? We'll walk through how we get this a little bit more either today if we have time or tomorrow, Thursday's class, right? And if we go out 2 standard deviations, well, even before we look at it, if I go out 2 standard deviations to the left and the right, is it going to be more or less likely I see a value in that range? Well, intuitively, if I'm creating a wider range, is it going to be more or less likely I see a value in that wider range? More. It includes the old range plus more numbers, right? So if I go 2 standard deviations above and below, there's a 95% chance that I see, if I choose an observation at random, it's somewhere in between 2 standard deviations of the mean. And then what if I go out 3 standard deviations? It should be even more likely, or the probability goes all the way up to 99.7. So if you select a data point at random, if it's 3 standard deviations away from the mean, that was a statistical improbability, right? It was very unlikely you should have seen a value that far away from the mean. In fact, in practice, we would maybe have real questions of that if that was a valid data point, right? Like it's pretty far. It can happen, right? There's a 0.0, there's a 0.3% chance that it could happen, but not very likely, okay? So we already talked about this. Oops. The way that we'll kind of start to notate this, if we have a normally distributed variable, we will say that this random variable X, we might want to know what its mean is. We might want to calculate some different things about it. We'll say it's normally distributed. This is this capital N. And then we just talked about, there's two things that define a normal distribution. What is its mean? Is its variance? So this would be X is normally distributed with this mean and this variance. So these would actually be numbers in practice, right? Now, a special case, which we'll use a lot, and we can convert any normal distribution into what we call a standard normal distribution. And then we can use these things called z-tables. Do these sound familiar? Yeah, right? So if I take a normal distribution, how do I get it so that it has a mean 0 and a variance of 1? So if I had a data set and I calculate it, let's say we'll do the height one. And I found the average height is, I don't know, 68 inches, right? How would I convert that height variable to have a mean of 0? I would take every observation and I could subtract what? The mean. Now when I calculate my new mean, if I've subtracted the mean from every observation, my new mean should be 0. How do I get, so my new standard deviation or my new variance is 1? I would actually divide, let's see, I have it here. Oh, I repeated my slides when I was copying and pasting from last week to this week. Where are we at? I'm skipping well ahead. There we are. So I subtract the mean, that gives me a new mean of 0 for my z-score, the standard normal distribution. How do I make sure it has a variance and a standard deviation of 1? I divide by the standard deviation. Right? So I'll show you how we do this in Stata before we leave today. We should have enough time to do this, but kind of jumping ahead just a little bit. Right? So the standard normal distribution, we'll eventually talk more about how do we get these z-scores. But once we do, we subtract the mean divided by the standard deviation. I can actually represent them to always be the same exact thing. If I have the mean, how many standard deviations away from the mean is the mean? 0. It is the mean, right? It's not far away at all. So these z-scores, the z-score for the mean will always be 0. Now, as I start to look at different values, right? Maybe if I'm thinking about human height, I'll just put some numbers to this here to make a little more sense. So let's say, well, I'll stack them. So let's say I have human height. I don't know. We're not worried about the gender thing here. Let's just say it's always the same for everybody. So let's say I had a mean of 68. Right? And let's say my standard deviation is 4, right? If I were thinking about, let's see, I chose someone at random and I see that they're 64 inches tall, right? Well, I know that the z-score for my mean should always be what? So these z-scores represent how many standard deviations away from the mean the value I'm looking at is. So if I'm looking at the mean, how many standard deviations away would that be? 0. If I'm looking at the value of 64, how many standard deviations away from the mean is that? Well, if it's 4 below, my standard deviation is 4. I'm 1 standard deviation below the mean, right? Or my z-score would be -1. What if I saw 76? That would be a z-score of what? How many standard deviations above the mean am I? 2. So that would be a z-score of +2. I'm 2 standard deviations above the mean. So we can convert any normally distributed variable into a standard normally distributed variable. Now it makes it easier for us to use those z-tables, right? Because now we've got the actual z-scores. Okay. Is this looking familiar, hopefully? All right. Any questions on this before we keep moving? Okay. So skip ahead just a little bit. We've already talked about this. Negative means we're going to be a certain number of standard deviations below. Positive z-score, we're a certain number of standard deviations above. So if I wanted to standardize variables, what would I do? Well, we already talked about Stata. I can calculate means and I can find standard deviations. I can create these new standardized values. If I standardize a value by subtracting the mean and dividing by the standard deviation, my new standardized variable should always have a mean of 0 and a variance or standard deviation of 1. So How do we do this in Stata, right? Let's see. So I'm gonna go here. Get my do file open back up. So let's just assume, I don't think it actually is, but just for the sake of this example, let's assume that packs per capita is normally distributed. In fact, I'll show you a quick way. It's not perfect, but you can get an idea of whether or not something. Also notice when I start typing, Stata is kind of helpful and identifies what variables already exist, and it tries to suggest things to me. So here, packs per capita was the variable I wanted. I'm going to use this hist command, right? What this does is it gives me a histogram. Okay, it's not perfect, but it kind of starts to give me an idea of like, is this at least somewhat normally distributed? It looks like it is, with like the exception of there's like some states with really high taxes, so that's kind of weird, but close to a normal distribution. So how can I standardize this variable of packs per capita? Well, I need to subtract the mean, and I need to divide by the standard deviation. So the first thing I'm going to do, yeah.
Is there a difference between?
I'm just short. I tend to in this class, when I'm giving you the commands, I'll give you the shorthand version. So for instance, hist and histogram will do the exact same thing. Just like EGen and eGenerate, well, I can spell, will do the exact same thing. I just typically will always give you the shorthand version. If you Google it, that's probably what you'll find anyways, and it just makes it a little bit easier. It's not as difficult to remember these long names. But if you ever have a question, if I'm going back and forth, by all means ask. But yeah, I typically will just kind of show you all you need, which is the shorthand version. Yep. Any other questions? Okay. So I'm going to create this new variable using my EGen command, where I'm calculating the mean of this packs per capita, right? So same syntax we used before. Calculate a new variable that is just the mean of that variable, and another one where I'm calculating the packs per capita standard deviation. So I'm going ahead and run these two. I'll now see that for every single state, I have this variable, which is here's the packs per capita mean, here's my packs per capita standard deviation. Okay. So if I wanted to standardize that variable, what am I going to do? Well, should be able to see everything here. I'm going to create this new variable, which is I'm only using math. I'm not using any built-in functions like the mean or the standard deviation here. So I don't need to use EGen. EGen just used these like built-in commands like calculate the mean for me, calculate the standard deviation. Here, I'm telling Stata what equation to use. I want to create this new variable. I'm going to call it packs per capita stand. Right? I'm standardizing that packs per cap variable. I want it to be so that it's standard normally distributed. What am I going to do? Well, I'll take every observation's value for that variable, packs per capita. I'm going to subtract the mean. Now, if I calculated this by hand, instead of putting the mean in here, I guess technically, well, I'll show you a bad way of doing this, and then I'll explain why it's bad. So let's say I just use the sum of, what do I want? Packs per capita. And I say, okay, the mean is 83.8. So instead of the variable here, if I were to put in 83.8, I can do that, right? And don't make these edits. I'm just going to show you, and then I'm going to go back to what I gave you originally in the code. But I'm using this to make a point, right? I could then also look at my standard deviation. It's 26.08. So, okay, I'm going to divide by the standard deviation, which was 26.08. I'm going to create this new variable. Now, what should be true is that when I summarize that standardized, if I've done it correctly, what should the mean of the variance or the mean of the standard deviation of a standardized variable always be? We said the mean will always be 0, and then the variance and the standard deviation will be 1. Remember, standard deviation is the square root of the variance. So if the variance is 1, the standard deviation is 1. Now, I go ahead and run this, and I'm like, yeah, I know I've done this perfectly. Okay, well, it's really close, right? Well, why is it really close? Because I was rounding things, right? If I actually use these variables I created, which was the actual mean, stored out to whatever decimal, I don't even know where Stata stops, right? And I also don't just use the rounded version of the standard deviation. So I use the actual standard deviation variable. This is going to be a lot more precise, which doesn't seem like it's going to matter much. But when we start to deal with like probabilities and like really large like tax revenue, being off by 0.001 can end up being millions of dollars if we're looking at the actual, so it does matter. We're trying to be precise. Don't use that sum command and type in numbers here. Calculate the actual values for the mean and standard deviation, save them as new variables. Now, if I try to create this variable again, it's mad at me. Why? Because I already created it, right? Now I'm trying to create it again using a different way. So if I ever make a mistake, there we go. I can use this drop command. Whatever I put next to the drop command. Oh, come on. Sorry. This mouse is more sensitive than that. There we go. It'll drop this variable that I've created. So notice this data exists, this variable exists, packs per capita stand. I want to get rid of it. So I'm going to use that drop command. The program tells me, okay, I dropped it. Sure enough, it no longer exists. Now, when I go back to my do file, now I can recreate that variable, right? So if I ever create a variable and I know I made a mistake, I can always use that drop command to get rid of it and then just run whatever I want to next. So I'm going to hit that. Now it's creating this using the more precise way. Now, if I summarize this variable, I'll see that the mean I get, yes, it's a little off, but this, because, stata stops at some point, but e to the -7. So the way we're going to have to start dealing with this a lot in this class. What would e to the -7 mean? That means move the decimal 7 places to the left, right? So anytime it's a really small value that can't kind of display it to you, it's going to go to scientific notation, which is essentially like times 10 to the 7th, but -7th, meaning move that decimal 7 places to the left. So this would be what? 0.0 or -0.0000001. It's basically 0, or a lot closer than when we were rounding, right? We got pretty close, but this is going to be even closer. And in fact, the standard deviation is so close, even with our rounding, we get that standard deviation of 1. Okay. Any questions on anything there? I see a hand over there. No. Okay. So this is how we would standardize variables in Stata. Okay. Any questions on that before we keep moving here? All right. So I think that should cover it for us. So a couple things more related to this before we get out of here today. I don't know. I have some like old data sets. Sometimes I'll just pull things in. This is another, I mentioned the histogram function. You can do something like create a histogram very quickly just to give you a quick snapshot. So human height here, I think I pulled out, even if you don't separate it by gender, looks pretty normally distributed, or at least really, really close. If I looked at, I saw this posted on Instagram a long time ago. It was like some CrossFit data, and like the total number of like reps. I don't know what this exercise was, but basically it's kind of interesting. Like anytime we talk about biology, human performance, human intellect, IQ, anything that's like biological, it tends to follow a really close to a normal distribution, right? So I saw this and they were like, oh, where do you fall in the percentiles? I don't give a shit. Like I just thought this was cool because like it's a great stats way of saying like human performance. I mean, this is almost a perfect normal distribution, right? I'm guessing there might be some like skill acquisition thing here, depending on what they had them do that caused this little bubble. But for the most part, we get this really nice normal distribution, right? So we see it pop up a lot. Why do we want then to standardize these normal variables? Well, we said we want these z-scores because in practice, what do we want to know? We want to know what's the likelihood that if I were to choose a person at random, say, what's the likelihood their IQ is in between these two values, right? Or what's the likelihood that their height is in between these two values? Or what's the likelihood their income is in between these two values? In order to do that, we need z-scores, right? Now, we can do that without z-scores. We've got a normal distribution function. It's just that then we would have to, well, I'll show you and then we'll end on this. So if I just keep things as a normally distributed variable, right? Even if they're normally distributed, and I forget even what the function is, but there's some function that is related. That's like 1 over the square root of 2 pi, something or other. There's some crazy function. Well, if you want to know what the probability that you're in between two values, what would I do mathematically? Find the area under the curve. How do I do that? Starts with an I. Integration. This function is nasty to integrate, so we don't want to do this every single time. So a good shortcut around that is if I turn a normal distribution into a standard normal distribution, a lot of those things simplify and the math is a lot easier. Not only is the math easier, there's a z table. Someone's already done the integration for us. Now, all we have to do is look up the z-scores associated with these two values. So we standardize these two values. Now we can look them up in a standard normal table. The table will tell us the area to the left. Well, if I know the area to the left of this value, I know the area to the left of this value, subtract the red from the green, and I'm left with what's in between, right? So makes our life a lot easier. We don't have to integrate every single time. Now we're gonna use the tables a little bit. Try not have two blue. Okay. So it's not like we're gonna be doing any integration by hand. We're gonna be using these tables a little bit starting out. For the most part, we're ultimately going to just start worrying about some of these cutoff z values. So we'll talk about things like confidence intervals, hypothesis testing. Do those sound familiar? Hopefully, yeah. So we'll be more interested in these cutoff z values, and then Stata will often give us some z values that we can kind of determine, are they past the cutoff point. In terms of actually calculating these z-scores, a lot of the times we're going to be relying on Stata to do that for us, right? But trying to give a background behind what we're doing, a little bit of review before we get to that point. Excuse me. So for next class, I want to point out a couple things. So one, we've got a lot of slides left here. So I'll probably go through these pretty quickly. It should still be review. In fact, some of this we've kind of talked a little bit about today. We'll talk about sampling. I'll run through a do file in which I'm going to do things on Thursday that I won't expect you to do, right? So Thursday's class will be a lot less Stata work that you have to replicate, more Stata work that I'm showing you really what the power of Stata actually is once we get done with this course if you wanted to continue, right? But we should be able to finish out or get really close to finishing out these slides. I also would expect that Thursday might be a good class period for me to use some in-class questions or use one of those in-class quizzes. I'm saying that. I'm running the course, so take that, what you will. Other than that, I may, in between classes, get the first problem set up just so you can start tinkering around with it. You'll have more than enough time to work on it, at least more than 2 weeks, but I might throw that up there. So if you see that and you want to start looking at it, you can. Okay. All right. Try to stay warm today, and I'll see you guys on Thursday.